All right, so today we're going to be jumping into our next section, which is section 9.8. And here really we're just going to be talking about higher order derivatives. Okay, for the most part, there's really nothing that's, I would say, outside the ordinary of what we've been doing up to this point. We're really just going to continue taking derivatives. So derivatives of derivatives, derivatives of derivatives, of derivatives. You can kind of see where this is going. And so let's just go ahead really quick and take a look at these notes. For the most part, we're really only going to be looking at, I would say, maybe 2 or 3 total derivatives that we're going to be taking in the purposes of this course. We really don't need anything beyond that. Here are some of the derivatives that we look at, and just for fun, I just decided to put all the higher ones so you could see what the names of them are. You'll see a nice little pattern here. The first derivative, generally in like a physics or engineering scenario, we generally think of that as like a velocity or like an instantaneous rate of change is what we've been using it as. For our second derivative, we usually treat that as a rate of change of our rate of change. So that's like our acceleration, okay? And usually it's so just kind of looking at velocity, think about like driving a car, right? We think of that as like miles per hour, right? There's a distance over an amount of time. For our second derivative, acceleration is our distance divided by our time squared. So that would be miles per hour squared. So it's kind of like an increase. How quickly is our velocity increasing? That's what our acceleration is. Third derivative, we call that jerk. The fourth, fifth, and sixth derivative, actually I misnamed that. I'll have to change that in the notes. That should be the sixth derivative. Fourth, fifth, and sixth derivative, these are going to be our snap, crackle, and pop. And I think that's, you know, us mathematicians have somewhat of a sense of humor, and that's your Rice Krispies breakfast cereal right there. So in any case, I just want to take a quick look at this example. And suppose we have a particle traveling according to this equation. Okay, so this equation is just our particle moving in a specific, I guess, orientation based upon this equation. And so this is representing the position of that at any given point in time. Okay, so kind of like up here when I was mentioning the first derivative's velocity and how, you know, if you think about it like miles per hour, if we didn't take any derivative of something, that would be representing our location, right? So miles. Then we divide it by time, so we get our miles per hour. Second derivative, our miles per hour squared, and so on and so forth. So S is the distance in feet. In this case, it's just going to be representing feet. T is the time in seconds. So the first derivative, or we call ds dt, the derivative of position with respect to time, is the velocity. And the second derivative, we usually indicate it with the, well, in the numerator, it's going to have the exponent, the second exponent tied to the differential, and then the time in the second derivative down below in the denominator is actually going to be squared, okay? So, and again, that makes sense because, again, acceleration is your time is squared in that denominator. So we want to find the acceleration at any given point in time. So really all we need to do is we need to determine what the second derivative of this function above is. Okay, and you can read through this, but basically we have this function, s is equal to 100t minus 16t squared plus 200. When we differentiate this, we take the derivative, we're going to get ds dt is equal to, again, that t goes away because we just have that coefficient in front connected to that variable that has an exponent of 1. So it's just going to be 100. And then we do 16 times 2 is minus 32. And then the t comes along for the ride. We reduce that exponent by 1. And the constant term goes away. So that's our first derivative. Now we need to figure out the second derivative. So the second derivative, we literally just take the derivative of our first derivative. So the second derivative is just going to be the derivative of 100 minus 32t. And you'll notice right here that it's just going to be looking right here at this part. The coefficient that sits in front of that t is just going to be minus 32. So what's interesting about this is that this first function that we have is a quadratic function. So it, in this case, it actually is a inverted parabola. So it has like a peak to it, a maximum. We're going to be talking a little bit about that in the next section. The second derivative is just a linear function, so it's just a straight line. In this case, it's decreasing, right? It's the slope of the tangent line or the velocity of that particle. And then the second derivative that we have here is just the acceleration. You'll notice that this acceleration right here is actually just a consistent value. It's just going to be a straight horizontal line. So it's just going to be a minus 32. So again, s of t, the original function, represents the position of s at any time t. The first derivative represents the velocity of that particle at any time t. And then the second derivative is just the acceleration. Okay? So it's constant everywhere. And again, remember when we're inserting units on this stuff, you have to make sure that you're utilizing the correct units. So because it's a second derivative, the time unit is always going to be squared, okay? And again, like I said, we're going to be jumping into, in the next section, the graphical connection between derivatives and the original function, second derivatives, things of that nature, okay? So what I want to do now is I just want to go through some examples. So let me go over to the whiteboard, and we'll go ahead and switch that over here. All right, so we're just going to go through some problems. Some of them, the early ones at least, you'll probably think are pretty straightforward, but that's hopefully the goal. And the goal is to make this a little bit more complicated as we move on. So for this first one, the first question is just asking us to find the second derivative, okay? So they give us f of x is equal to, let me fix that equal sign. There we go. F of x is going to equal 2x to the 10th minus 18x to the 5th minus 12x to the 3rd plus 4. Okay. So the first derivative is just going to be f prime of x, and we can use the properties of taking the coefficient, multiplying by the exponent, reducing it by 1. So 2 times 10 is 20. And we're going to reduce this exponent by 1, so it's going to become a 9. 18 times 5, this is going to be a minus 90, x to the 4th. Then we're going to have 12 times 3, which is a minus 36. We reduce the exponent by 1. And we'll notice that the 4, because it's a constant term, its derivative is just 0, so we can ignore it. All right, now we can go ahead and take a look at the second derivative. So 20 times 9 is going to be 180, and we reduce the exponent by 1. 90 times 4 is this is going to be a minus 360, x to the 3rd. Minus 36 times 2 is going to be a minus 72, x to the 1st. So I'm just going to leave it at that. Excuse me. All right, let's do another one. I'm going to go ahead and do this right here because I think I've got enough space. So suppose I've got g of x is equal to x cubed minus 1 over x, okay? My suggestion on many of these problems is that if you have something like this in the denominator, that what you do is you modify it so the exponent becomes negative and you just flip it to the numerator. So in other words, this is the same thing as x cubed minus x to the minus 1, okay? And the reason why I suggest that is generally it's just easier to take derivatives if you've got simple variables like this with negative exponents. You can use the same property across the board, whereas with this, if you've got higher exponents or things like that, you may have to do like a quotient rule, and that's just annoying if I'm being real. So save yourself some frustration and just make your life easier right off the bat. All right, so the derivative of this is going to be a 3x squared, and this is going to become a plus x to the minus 2. The minus 1 times the minus is the plus, and then we just reduce the exponent by 1, so that becomes a minus 2. And now I can do the derivative again, so the second derivative of this is going to be 6x minus 2x to the minus 3. Now, I might suggest just right off at the very tail end, you can leave it in this form. I don't know if your homework is going to give you problems if you just leave it like this. So in case it does, you can just convert this back into something that looks like our original form. And so this is just going to become a minus 2 over that x to the minus 3 is going to become an x cubed down in our denominator. Okay, so this is going to be our solution right here for that problem. All right, let's go ahead and do another one. Let's do this one. Suppose I've got y is equal to 3x squared minus the cube root of x squared. Okay, and again, same idea as the previous question. In that previous question, we had just a rational part of that function. And so we wanted to modify it so it had a positive, or I should say it had a negative exponent, but it was something that was just in the numerator. We can do the same thing here with this problem. And again, this is why it's really handy to know these properties of exponents, because you can really modify the questions and make it a lot easier. Just something to remember here, that 3, if you think about it like a division, really that's kind of what we're doing when we're looking at roots. Okay, you take the index and you divide it by whatever the index is. So in this case, this is going to be a 3x squared. Okay, and then this next part is going to be a minus x to the 2/3. Okay, that 2 is the numerator, and that in that exponent, I should say, because it's tied to that x, and then we're just dividing it by 3. So that's where that 2/3 comes from. Okay, so again, like this is really handy to convert. So if I had, say, for example, this is kind of like a little side note here. If I have, say, like the 6th root of x to the 5th, this is the same thing as x to the 5/6. Okay. So anyway, just an idea. Or you could even do the opposite. So if I have the 4th root of x to the 7th, this is going to equal the same as x to the 7/4. Okay. So in this case, the fraction is actually bigger than 1. Over here, the fraction's smaller than 1. But the same property applies. So this is in our denominator. You can see that right there. This is our denominator. And then our numerator is going to be this guy. Okay. So same idea here. There's our numerator. And then this is going to be our denominator. Okay. So if you know how to do that, it's going to be really just to your benefit as we work on future problems. But in any case, let's go ahead and take a look at this next one, or the derivative then. So the first derivative of this, 3 times 2 is going to be 6. And then we reduce the exponent by 1, so it's just going to be 6x. For this one now, I'm looking over here at this problem. 2/3, I'm bringing it down in front, so this is going to be a minus. That stays along for the ride. We multiply by a 2/3. And then we have to reduce this by 1. Now, common issue with fractions, a lot of times what people will do is, if you take like a half and you subtract 1, it's a minus 1/2. But that really only works with like the 1/2. A lot of times people will do this. They'll take the 2/3 and subtract 1, and it's, oh, it's a minus 2/3. It's actually not. If you subtract 1 from 2/3, you're going to get a minus 1/3. Okay, so just make sure you're double checking your arithmetic on some of these problems, because it would be really silly if you got something like that incorrect. Just all you'd have to do is literally just try the addition or write the addition out. So don't fool yourself. All right, 6x, the derivative of this is going to be 6. And now we've got the 2/3 times the minus 1/3. This is going to be a plus, 2 over 9x, and we're subtracting 1 from 1/3, so that's going to become a minus 4/3. Okay, and if you wanted, again, similar to what we did in the last one, if you want to convert to something that's kind of rational radical form, I guess, this 2 is going to be in the numerator, and then the 9 is going to drop down as the fraction. So again, this is all multiplying here. This x to the minus 4/3, it becomes 4/3 in the denominator. And remember, we're taking the cube root because it's going to be the bottom of x to the 4th. So this right here is an equivalent expression to that thing right there. Okay? So I hope that makes sense. If not, then go ahead and take a look here, or go back to the early stuff that we covered to look at some examples of that, just as a practice. All right, let's go ahead and jump to our next problem. So on this one, they're asking us to find the fourth derivative. The fourth derivative. So we want to find f, and here they write it like this. If, say, my first function, my original function is 7 over x, okay? Which, by the way, remember, this is the same thing as 7x to the minus 1. So now we just have to start working on our derivatives. So our original function is that. So our first derivative, this is going to become a minus 7 x to the minus 2. The minus 1 times the 7, and then I reduce the exponent by 1. The second derivative here, I'm going to take the minus 7, multiply it by the minus 2, and I'm going to get 14. And I'm going to reduce this by 1 again. Third derivative, I'm going to write it as 3 primes there instead of just the 3, but you can do it either way, it's fine. 14 times a minus 3 is going to be a minus 42. And this is going to be x to the minus 4. And then f4 of x. Now we do it one more time. So we're going to get minus 42 times a minus 4. This is going to be 168, I believe. X to the minus 5. And again, since we want to get rid of those negative exponents, this is just the same as 168 over x to the 5th. Okay. All right. Let's take a look at the next one. Okay. Ooh, this one's interesting. So they are asking us to find f triple prime of x if f prime of x is equal to x squared all over x squared plus 1. All right, so on this one, they went ahead and did us the favor of finding the first derivative. So actually, we start with the first derivative. We have to do the second derivative and the third derivative to get our solution. So there are a couple ways to do this. You could convert this thing into something raised to the minus 1, then use the chain rule with a product rule. Or what I might suggest doing is just using the quotient rule right off the bat. It just might make it a little bit easier. So the second derivative of this, and again, remember the song. This is the phrase or song, whatever. Low d high minus high d low over square of low we go. Low d high, so this is going to be a 2x times x squared plus 1. So low d high minus high d low. X squared times 2x. All over the square of low we go. X squared plus 1 squared. Okay. All right, so let's simplify this because obviously we have to do another derivative, and trying to do a derivative of that looks like a absolute nightmare. So here we're going to get 2x cubed plus 2x minus 2x cubed. Hey, look at that. Those cancel. And then actually, I'm going to multiply this out because taking the derivative of that is just going to be like a chain rule. And you can do it if you want. I just don't want to be honest with you. And multiplying this out isn't really as complicated as doing the chain rule. So I'm always about, like, as you get to like higher level math, I know like most teachers probably that you've ever had have said, like, don't be lazy, work hard. In mathematics, it pays off to be as lazy as you possibly can. So I embrace it. I say work smart, not hard, if you can take it. So here, we can just FOIL this out if you want. There's a quick little trick to do it, and that's using Pascal's triangle. I won't get into that. You can look that up if you want, but if you have a binomial expansion, if you want, you can search Pascal's triangle binomial expansion in YouTube, and you'll see tons of videos on it, I guarantee it. But in any case, this is just going to become x to the fourth plus 2x squared plus 1, okay? So that's just the expansion really quick. And you'll notice what happens. This thing and that thing are going to cancel out, so I don't have to worry about that. Now when I do the third derivative, I can do a quotient rule again, and taking the derivative of this is going to be much easier than the derivative of that. So you can do it again. Either way, it doesn't matter. I don't really care. I guess whatever floats your boat. Low d high. So we've got x to the fourth plus 2x squared plus 1 d high, so this is 2, minus low d high minus high d low, 2x d low, derivative of the bottom, so that's 4x cubed plus 4x, all over the square of low we go. Squared plus 1 squared. All right. And let's go ahead and simplify this if we can. I think we can. So we get 2x to the fourth plus 4x squared plus 2 minus 8x to the fourth minus 8x squared. There's a minus in front, so every term that I multiply has to become negative, so that's why that works out that way. And I'm just going to leave this alone. Binomial expansion with exponents is pretty easy. Trinomial expansion is not very fun, so I'm not going to do it. I'm just going to leave it like that. Okay, so here we've got 2 minus 8 is a minus 6 x to the fourth, and then we've got a 4x squared minus 8x squared, so this is going to be a minus 4x squared, and then we've got the plus 2 at the end. All divided by x to the fourth plus 2x squared plus 1 squared. Alrighty. How about that? All right, let's go ahead and do another one. So that was doing the third derivative given the first. Let's go ahead and look at a problem that's a little bit more of a business application. So I think I mentioned it before, but there's things such as cost functions, revenue functions, and profit functions. Profit is merely just your revenue minus your cost. In this instance here, in this problem that we're going to be looking at, it says this: the revenue in thousands of dollars from the sale of a product is given by this equation. So R is equal to 15x plus 30 times 4x plus 1 to the minus 1. Oh, it was so convenient of them to include that. right here, so we didn't have to convert it. So nice. All right, minus 30. So this is our revenue function, where X is the number of units sold. So if you throw an X value in, any X value, so if you throw in like a 50, you'll get a revenue that's kind of associated with that number of units sold. So part A is asking us, at what rate is the marginal revenue? So anytime you think of or hear the word marginal, you have to think of derivative, okay? So marginal revenue, marginal cost, marginal profit. If you're given a function, profit, revenue, or cost function, all you do is you just take the derivative of that, and that's the associated marginal function, which is our derivative. So not too tricky. So at what rate is the marginal revenue changing? Okay, so you have to kind of think about this logistically, right? They're asking us for the rate at which the marginal revenue is changing, not our revenue. So the rate at which our revenue is changing would be the marginal revenue. The rate at which the marginal revenue is changing would be our second derivative. So that's kind of what this is asking in kind of fancy business language. What's the rate at which the marginal revenue is changing, or how quickly is it accelerating, right? When the number of units being sold is 25. Okay, so first we have to figure out what the marginal revenue is. Okay, so we've got this fancy marginal revenue with a line. This is just going to be 15, and then we do the derivative of this. So minus 1 times 30 is a minus 30. Okay, and now I'm going to rewrite the inside. Again, this is just the chain rule to the minus 2. We lower the exponent, and then we have to take the derivative of the inside. Okay, so this 4 is the derivative of 4x plus 1. The minus 30 goes away, so we're all set. So I'm just going to rewrite this as 15. 4 times 30 is minus 120. This is going to be times 4x plus 1 to the minus 2. And so now I need to figure out what the marginal revenue, I'll just call it marginal revenue prime because it's like the marginal revenue. So the second derivative of that revenue function is going to be minus 30 times a minus 2. Okay, whoops. Sorry, here we go. I'm looking at the wrong one. Minus 120 times a minus 2 is going to be a plus 240. Okay. 4x plus 1 to the minus 3 now. And then we multiply by the derivative of the inside again. Okay, that's just the chain rule. So 240 times 4 is the same thing as 960 times x, 4x. 4x plus 1 to the minus 3, which, by the way, is the same thing as 960 all over 4x plus 1 to the third, okay? All right, so x is the number of units, and what they're doing is they're asking us in the very first part that we need to figure out what the rate of the marginal revenue is changing when the number of units being sold is 25, okay? So I'm subbing 25 in for x here in this second derivative. So we're going to get, this is again for part A, 960 divided by 4x, 4 times 25. Let's just put the value in here. 25 plus 1 to the third. And you can go ahead and punch this into like a calculator or Wolfram Alpha, that's fine. And what you're going to find is that this is approximately equal to 0.0009, okay? It's a very, very small quantity. So that's part A. Part B is asking us that we need to figure out, interpret the result of part A. Okay, what is it saying? So what it's saying is when the next unit is sold, the next unit is sold, the marginal revenue Okay. The marginal revenue will increase by about, this is a dollar amount, I should point out. So in other words, if you think about this, this is going to be roughly 90 cents or 0.90 cents. Come on. This is so slow right now. 90 cents per unit. It's not 90 cents, it's 0.90 cents. So it's a little under 1 cent, okay, which is a fraction of a cent. That actually is a thing in economics and business. They actually do use that, so just to bear that in mind, okay? All right. If you have any questions, feel free to let me know, but this is really all we have for today, and hope you have a great day.